So, first things first, this is kind of common sense, I guess. Okay, if we have a polynomial, then there has to be a zero. Okay, in the complex number system. Now, remember, real numbers are in the complex number system, right? And we know from when we went through that green packet, if it's a third degree polynomial, we're going to have 3 zeros, right? Well, now we're going to look at polynomials that we can have real zeros, we can have imaginary zeros, okay? So if we have a third degree polynomial, it's possible that some are real, some are imaginary. It's possible in like a fourth degree polynomial, they all could be imaginary zeros, okay? But in the complex number system, which include real and imaginary, and the combination, okay, we are going to have a zero. Okay? That's what this says. To us, we kind of feel like, oh, well, yeah, duh, right? But now we've made it official. We've been working a lot with factors, yes? Okay. A part of your quiz, you had to write your polynomial as factors, right? I think there's like 3 factors for that one, right? Okay. One thing that I want to talk about is it's called the linear factorization theorem. Okay. How many zeros are we going to get if we have an n degree polynomial? There's going to be n zeros, right? So if we have an n degree polynomial, we will have n zeros, and we know that with each of our zeros, we can write a factor, correct? So, however many zeros we have, that's how many linear factors we are going to have. So an n degree polynomial will have n linear factors. Okay. What does linear mean in this linear factor? Okay, so those are linear factors. Okay. So it's going to be your job in some of these problems to find all the zeros and then write your polynomial as a product of linear factors. However many zeros you find, you're going to take those and write them as linear factors. Okay, so I'm going to show you what that would look like. Are you ready? All right, so let's say that these are your zeros. F of x has zeros of 1, -2, 3i, and -3i. Then I want us to write the linear factors of f of x. So if 1 is our 0, our linear factor is? If -2 is our 0, if 3i is our 0, and if -3i is our 0. Right? There's our product of linear factors. Okay? If we are working towards writing linear factors, you first have to find all of the zeros. Okay? Or factor it all the way down if you can. There are going to be some problems where we can factor just right off the bat, especially if it's like a quadratic that factors nicely, or a cubic function that we can factor by grouping. We're going to be able to factor some of these, But for some of these, we're going to have to find zeros and then write the factors, okay? So it just depends on the situation. Now, we're going to talk about the rational zeros test. The rational zeros test is something that you did last year, and you're all going to remember what I'm talking about as soon as I describe what it is, okay? The rational zeros test is a list of numbers that we use to guess and check our zeros. You know what I'm talking about a little bit? Maybe, maybe not. Okay. As soon as we go through an example, I think you're going to remember. Okay, so first of all, in the last section, I would say, hey, this is a factor, verify that it's a factor, and then find the rest, okay? Well, what if we don't have that factor to verify, okay? Like I said, there's going to be some of these problems that we can factor right off the bat, but there's going to be some that we don't have the tools to factor. So we need to figure out our zeros, okay? Well, we can't just start guessing and checking random numbers, okay? We don't want to start with a pool of an infinite amount of numbers to start guessing and checking, all right? But there's this thing called the rational zeros test that says if we have a polynomial, this is just a polynomial, with integer coefficients, then every zero that is rational, what does rational mean? Kind of on the right track. Any number that can be written as a fraction, okay? Irrational are those like square roots or like anything with radicals, pies, okay? So if we have a rational zero, then it's in the form of a fraction. What are these p's and q's, okay? P is a factor of the constant term. This is the constant term. And Q is a factor of the leading coefficient. You don't have to write this down word for word, but write down what you need to. Okay? If we have zeros that are rational, then they are in the form of P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. Okay, so time out. Here our zeros are 1, -2, 3i, and -3i. 1 and -2 are rational numbers. Those are our rational zeros. Okay. So what we can do with this information is we can create a list of possible zeros based on that criteria. And we can narrow down our infinite pool of numbers to just a little kiddie pool of numbers, right? That we can check using synthetic division to see if they work in our function or not. Okay, so this gives us a way to narrow down our options so we kind of have somewhere to start as far as checking for zeros. Okay. So if we are given a polynomial that we can't factor, we're going to use the rational zeros test to write a list of numbers that involve this criteria. So we can figure out, okay, what are factors of the constant term, what are factors of the leading coefficient, and we can create all these fractions, okay, and then we can start using those numbers to check and see if they're zeros. If we check and it's not a zero, we'll cross it off our list and move to another number. Is synthetic division time consuming? Not really. Okay, it's pretty quick and painless, right? As long as you're careful with your arithmetic, okay? So you're going to want to do your homework in pencil, first of all, because you are going to check zeros, and some of them are not going to work, some of them will. Okay. You guys ready for an example so you can kind of see what I'm talking about here? Okay. Please write this problem down. Okay, so the rational zeros test says that our rational zeros are in the form of P over Q. So first of all, we're going to figure out our possible zeros. So they're in the form of P over Q. P are factors of what? Our constant. What's our constant? What are factors of 3? 1 and 3. Okay? Now, I want you to also realize, though, that we could have a positive or a negative 1 and a positive or a negative 3, because negative 1 times negative 3 is 3. Yes? It's a factor of 3. Okay? For our denominator, what are factors of 2? 1 and 2. And we also have to account for the negative, because negative 1 times negative 2 is 2. Okay? So let's write our fractions out. We have 1 over 1. We have 1 over 2. We have 3 over 1. And we have 3 over 2. Okay? We have narrowed our rational zeros to 8 possibilities. Okay? That seems like a lot, but it's not if you compare it to infinity, right? Mm-hmm. Okay. So these are our possible rational zeros. So now what we can do is we can set up our synthetic division. 3, negative 8, 3. And if we have a 0, when we plug it into synthetic division, what's going to happen?
No remainder.
We should get no remainder. Okay, so that's our goal. The 2 comes from the leading coefficient. We wrote down.
Like the second part, like where it
Oh, that was supposed to be 1/2. I said 1/2, didn't I? And I wrote 2. Thank you for catching that. I said 1/2 and didn't write it. Okay. Are we good now? All right. So, what would you like to try first? Let's try 1. Let's try 1. Bring down the 2, multiply to get 2, add to get 5, multiply 5 times 1 is, you lucky dog. Matt guessed the 0 on his first try.
Yeah.
Ugh.
all the zeros.
If that wouldn't have worked, we would have had to cross them off our list and try another one. My advice, always start with 1 and negative 1 because they are the easiest to multiply. Okay? Always start with 1 and negative 1 because they're the easiest to multiply. Okay, so we have found a 0. Yay! Now what can we do? We started out with a cubic function. We are now down to a quadratic. So what we have left is 2x squared plus 5x minus 3. Right? And we know that this is still times x minus 1 because 1 was a 0. Right? Okay, so let's factor this right here. Okay, everybody on your papers, please factor this. Everybody like 3 different methods that people use, so I'll let you do your thing. Grant, what does it factor to?
X plus 3 times 2x minus 1.
Do you agree? I feel good about it. Okay? So that means our zeros are x equals 1, x equals 1/2, and x equals -3. Hey, were those in our list? Yeah, they were. Nice. So if we would have tried 1/2 first, which we wouldn't have because we probably would have saved that for one of the last ones, right? But if we would have tried 1/2 first, we would have gotten 0 and we could have factored that one. Alright. Okay, so this is something, is this now kind of coming back from last year? Okay, do your homework with a pencil. If you start with a 4th degree function, you will have to do synthetic division 2 times to get it down to a quadratic. Okay, so whatever you have as your list of numbers, okay, you can keep using that, or you can make a new list of numbers with, after you find 1 0, you can make a new list of numbers. Okay, keep in mind that zeros can repeat. Okay. So when you're finding multiple zeros, just keep that in mind. Okay. Now, we need to talk about complex zeros. Okay, the other day we talked about complex numbers, and it felt very just random, right? Okay, how does that tie in with all of this stuff? First of all, if we have a complex zero or an imaginary zero, what does that mean graphically? Okay, we're not going to cross the x-axis there. Okay, so if we get an imaginary zero, we know it's not crossing the x-axis. Okay, it's possible for a parabola not to cross the x-axis. In that case, there are 2 zeros, but they're imaginary. Okay, it is important for you to know that if we have complex zeros, they will always come in conjugate pairs. Okay, so you saw our first example where we had 3i and -3i, those are conjugates. Okay, if 1 plus 2i is a 0, then 1 minus 2i also has to be a 0. Okay, if we have a polynomial that has an imaginary or a complex 0, it will come in complex pairs. Okay, there will always be 2 of them, and they will be conjugates. Excuse me, they will come in conjugate pairs. If you think back to those problems you did in your homework with the quadratic formula, like this one on the board, it's a conjugate pair, right? Always going to happen like that. If there are imaginary zeros, there will always be an even number of them. So you will have 2 of them, or 4 of them, or 6 of them. We probably won't look at any with that many, okay? But keep those things in mind as we start to think back to what the graphs look like, okay? Tuesday's a really fun day next week because we're going to take like the past 4 sections and put them all together where we talk about the coefficient test and the zeros on the graph and multiplicity, and we're going to do everything all together, all right? So look forward to that. Now, what does this mean as far as today? Okay. Here I have a 4th degree polynomial. But I have told you that 1 plus 3i is a 0. I would like us to find all the zeros. Well, we know 1. Do we know anything else? 1 minus 3i is also a 0. How are we going to find the rest? Synthetic division? What? Okay, we can do synthetic division with 1 minus 3i, and then do synthetic division with 1 plus 3i. Is that our only option? Matt, you're shaking your head. What's our other option? We could. What we could do is we can take these two factors and multiply them together and do long division that way. Okay? What would you like to do? 2 sets of synthetic division, or multiply 2 factors and do long division? Long division is what I'm hearing. Okay. So here we know that x minus 1 minus 3i and x minus 1 plus 3i are factors. And when we multiply conjugates, we know that those imaginary numbers are going to go away. Okay, so that's what makes this nice. So let's go ahead and multiply this out. It's kind of a pain, but it'll be worth it in the end because we're going to get those imaginaries to cancel. So x times x. X times negative 1. And then x times 3i. Then we're going to take negative 1 times x. And negative 1 times negative 1. And negative 1 times 3i. And then we will take negative 3i times x. And then negative 3i times negative 1. And then negative 3i times positive 3i would be negative 9i squared. Can I write positive 9? All right, ladies and gentlemen, what happens? 3ix goes away. 3i's go away. And we're left with x squared. Excellent. Why did we do that? Because now we know that this should divide evenly into f of x. You ready? Oh, I lost that second. X to the 4th minus 3x cubed plus 6x squared plus 2x. Okay. And we're going to divide x squared minus 2x plus 10 into that. Okay. This should divide evenly because we used zeros to write that quadratic factor. Okay. So if you get a remainder that's not 0, you've done something wrong. Okay. How many times does x squared go into x to the 4th? Okay. So we have x to the 4th minus 2x cubed plus 10x squared. Remember, ladies and gentlemen, we are subtracting. We are subtracting. So what are we left with? Careful. Negative x cubed minus 4x squared, right? And then plus 2x. Excellent. X squared times what is negative x cubed? Negative x. So we have negative x cubed plus 2x squared minus 10x. Right? We are subtracting. What are we left with? Oh, you You read this right here. When we do our subtraction.
Negative 6x squared plus 12x.
There we go. John, did you see what you're looking at?
Yeah.
Okay. Last time, we just brought down the constant term. So x squared times what is negative 6x squared? Negative 6. And if we do divisor times negative 6, look at that. We get our remainder of 0. That should happen, right? So, what we have left, when we divided out those imaginary zeros, is x squared minus x minus 6. What does that factor to? Okay. So our zeros. 3, negative 2,
Something plus.
1 plus 3i, and 1 minus 3i. If you want to write them in conjugate pairs together, you can. If you want to write them separately, you can. Okay, I don't care. I'll take it either way, but those are our zeros. Okay? If we know one imaginary zero, we know the other one. They have to come in pairs. Alright. The pep rally schedule is eating 5 minutes of our time. Okay? But here is your homework. Not that many problems for you this week. Okay? Not that many. Please be patient as you're doing your assignment. Okay, today Matt guessed a 0 right away, and we didn't have to erase and start over. That's not going to happen every time. Let's be realistic. Okay, so be patient. Be careful with your arithmetic. I would hate for you to try a 0 that really works, but then you go so fast through it that you misadd, mismultiply, and you blow right past it. Okay? Please make sure you're filling out your surveys. If you forgot to fill out the surveys and you did your homework last night, fill it out right now while we're waiting for the bell to ring here in 1 minute. Okay?